Hi everyone. So far in all lectures on vibrational spectroscopy, we have discussed diatomic molecules, we have discussed anharmonicity and their effects. Most of the molecules that we deal with in chemistry are polyatomic. That is, they consist of more than two atoms. It is obvious that a diatomic molecule can only be linear and can have only one normal mode of vibration. But in the case of polyatomic molecules, there are more than one kind of vibrations, and we refer to these modes of vibration as normal modes. So let's consider a molecule consisting of n atoms has multiple normal modes of vibration. In general, molecules can be classified as nonlinear molecules and linear molecules. Let n represents the number of atoms in the molecule, then a nonlinear molecule has 3n minus 6 normal modes of vibration, whereas a linear molecule has 3n minus 5 normal modes of vibration. The simplest of the polyatomic molecule with more than one bond is a triatomic molecule. We will discuss the nonlinear molecules with the example H2O, and we will discuss the linear molecules with the example of carbon dioxide. Let's start with the nonlinear triatomic molecule H2O, which has permanent dipole moment. Since it has 3 atoms, the total normal modes of vibration is given by 3 into 3 minus 6. That is 3 normal modes of vibration. They are namely nu1, nu2 and nu3. In nu1 mode of vibration, we can see the symmetric stretching. It involves a change in dipole moment, hence it is IR active. And peak corresponding to the excitation of nu1 mode can be seen in IR spectrum, and this symmetric stretch causes absorption at 3652 cm inverse. Another normal mode of vibration of H2O is symmetric bending or scissoring. It also causes a change in dipole moment, hence IR active, and shows an absorption peak at 1596 cm inverse. Here we can see the asymmetric stretching of vibration, and it is also IR active, and it shows an absorption peak at 3756 cm inverse. When we analyze the spectra of water molecule, we can see 3 peaks, including the peak of symmetric bending, that is at 1596 cm inverse, and the symmetric stretching peak, that is at 3652 cm inverse, and we can see the peak corresponding to the asymmetric stretch at 3756 cm inverse. Now let's consider the vibrational modes of carbon dioxide molecule. As carbon dioxide consists of 3 atoms, we have 3 into 3 minus 5 modes of vibration, that is 4 normal modes of vibration. And we know that carbon dioxide has no permanent dipole moment. So here we can see the normal modes of vibrations of carbon dioxide molecule, namely nu1, nu2 and nu3. You may think like there are only 3, right? Let me tell you why. So prior to that, we just have to look into the first mode of vibration, that is nu1. Here we can see the asymmetric stretching of the bond, and therefore there will be no change in dipole moment. So it will be IR inactive, and hence it will not produce a line in the IR spectrum of carbon dioxide. In nu3 mode of vibration, we can see the asymmetric stretching, and it involves a change in dipole moment, hence IR active. It shows an absorption peak at 2350 cm inverse. And there are 2 more mode of vibrations, namely bending. Among these, one is in-plane bending. So it produces a change in dipole moment and hence IR active. Another mode of bending vibration is out of plane bending, which also involves a change in dipole moment and hence IR active. And these two bending vibrations have the same frequency and they shows a single peak at 667 centimeter inverse. Since they have the same frequency, they are said to be degenerate. When we analyze the carbon dioxide spectra, we can neglect this part. This indicates the presence of water as impurity. Here we have only two peaks. The peak corresponding to the symmetric stretch, that is at 1347 centimeter inverse, is absent because it is IR inactive. The peaks corresponding to 2350 is shown and the peak corresponding to the bending vibrations at 667 centimeter inverse is also shown.